let me thank Guillermo and Carles for organizing this unusual and impressive meeting, and for prompting me to look at finitely evaluated logics from a very positive viewpoint. Well, I will be speaking about 0-1 laws in many evaluated logic. So this talk is very close and has a strong intersection with Professor Greidel's talk that we just hear. Let me start recalling the classical 0-1 law that Professor Greidel explained some minutes ago. But I want to stress that there is a not very well-known extension of original Fagin's 0-1 law by Overshelp, in which we work not only with all the structures, we don't work with all the structures, but we work with a class of structures which satisfy some kind of axioms that we call parametric conditions. So we work with a class of relational structures finitely infinite defined by a parametric sentences. And for that class, if we take the models with domain, the natural numbers between 0 and n, then we have this very well-known law that says that if we take the fractional probability, the counting probability, then it converges to 0 or 1 for any first order sentence. Parametric sentence is one which is equivalent to a conjunction of universal formulas of the form for every sequence of distinct variables, phi holds, where phi is a quantifier-free formula without identity, where all the atomic formulas share the same variables. For example, irreflexive symmetric graphs are described by a parametric sentence, but transitive graphs are not described by a transitive sentence, by a parametric sentence, excuse me. The counting probability we have used in this statement of the 0-1 law corresponds to assigning probability 1/2 to the atomic relations. But it's well known that we, as Professor Greidel explained also, that we may use any probability. In this case, I will take a probability which is different from 0 and 1, positive and less than 1. If we take this probability, we get again the 0-1 law, but a very important fact, we get the same we get the same probabilities, okay, for the sentences. The limit 0 or 1 for a sentence phi is independent of the probability we use for the atomic formulas. It is well known also that the 0-1 law holds for variable bounded infinitary logic, the fragment of L omega 1 omega, where the formulas contain only finitely many variables. And there is a wealth of positive and negative results pertaining to the case in which the probability of atomic formulas depends on n, on the size of the universe. We will be considering generalization of these laws to many valued logics. Well, this is a short reminder of what are we speaking of when we say many valued logics. I will fix an algebra which has a lattice reduct. The reason I am fixing a lattice reduct in the algebra is just to interpret quantifiers in the tradition of logic, in the logical tradition. The language is built in the usual way from variables and relation symbols in the vocabulary, using connectives corresponding to conjunction and disjunction and all the other all the other operations on the algebra. I won't put any any condition of the other operation. Maybe we don't have any. Maybe we have many others like negation, implication, etc. Models are just A-valued models for the algebra A. So every relation symbol determines in the model determines a map from to the arity of the relation into the algebra. And for each formula, then we get inductively an associated map from the k power, where k is the arity of the number of variables, into the algebra, which for this we interpret atomic formulas according to M, connectives according to the algebra, and quantifiers as suprema and infima. And then we fix the class of models with domain the natural numbers between 0 and n. Okay, and then we may define asymptotic probabilities for finite A, very much in the way that Professor Gradle explained for his semi-ring semantics. So we fix a formula and we fix elements, numbers less or equal than n, and we fix an element in the algebra A and define the probability of the formula takes the value A in those elements, in those arguments, just by taking the fraction. That corresponds to the probability that a randomly chosen model in this class of finite models assign the value A to the formula. This corresponds also to assigning the equiprobability 1 over the cardinality of A to any atomic formula in the random model of n elements. We may choose instead any probability distribution in the algebra. Remember that we are thinking of finite algebras. Then we may ask the distribution to assign positive probability to every element of the algebra. That will be the only condition I ask of the distribution. It's a distribution probability that assigns positive probability to any value. Then it assigns positive probability to the event that an atomic formula takes the value A. In any case, we get a many-valued 0-1 law that may be expressed in two different ways. The first way you may express it is that for any sentence phi and value A, true value A, the limit of the probabilities in the models of n elements, the probability that phi takes the value A is 0 or is 1. There is another way in which you may express this law, which is equivalent, that it is that for every formula phi, sentence, phi, there is a unique value A such that the limit probability that phi takes that value is 1. The equivalence between both statements of the law is an easy consequence of probability laws, and the fact that every sentence has to take one and only one value in A. So there is no mystery in the equivalence of these two formulations of the many-valued 0-1 law. Now, this law is an easy law, and in more interesting, it follows from the classical law via a simultaneous translation of any sentence, any formula in the language of the A-valued logic into classical logic, only that we change the vocabulary tau to a vocabulary which multiplies every atomic symbols as many times as elements are in the algebra. The intuitive idea of this translation that I will explain later is that if R represents an atomic formula, R super A represents the classical atomic statement that the atomic formula takes the value A. That's the idea of this multidimensional translation. Actually, a translation for every value in the algebra. And there is a corresponding model transformation from models, A-valued models, into classical models on the vocabulary that multiplies tau. The model translation is very simple. It's the translation that just associates to interprets the formula R super A, the atomic formula R super A, just as the set of elements of the model where the original atomic formula takes value A. This is what I explained before. For these two transformations, the syntactical one and the model theoretic one, it's very easy to check by induction in formulas that the value of a formula theta in a tuple of values I1 through I case is A in the original model, if and only if in the classical model, the corresponding translated formula is true. Let me explain the translation. I won't say too much about it, only that it just captures the idea that the formula super A expresses the classical fact that the original formula takes the value A in the original model. Then the image K of this model transformation, it's very easy to see that this is axiomatized by the parametric sentence that says that anatomical formula R super A holds for some value A in the algebra. So I am saying that every atomic formula in the original language has to take a value in A, and the parametric formula saying that only take one of these values, which is the second formula here. Moreover, the measure induced, the original measures that we are using for the many-value law here, for the original A-valued models, induces may be translated to the K models, to the models in K, in the image of the transformation, and it's very easy to see that the probability in the models with n elements that phi take the value A is identical to the probability in the classical class of models K of the translated formula phi super A. As K satisfies the 0-1 law because it's parametric, then the 0-1 law for the many-valued 0-1 law follows immediately because then the mu n of phi, the probability that phi is equal to A, is identical to the probability of phi super A, which has to take value 0 or 1 because K satisfies the classical law. Now, the equivalence of this formulation with the second, as I said before, is just a matter of basic probability. Okay, it's clear from this explanation that the 0-1 law holds not only for classes of for the class of all A-valued structures, finite ones, but also for classes of A-valued structures which are defined by conditions which are parametrically expressible in the target language of the translation. Maybe there are many properties that perhaps you cannot express in the original logic because we don't know which is the strength of this logic. Maybe its expressive power is very poor. But anyway, we may express things in the translated language. Perhaps we may express in the translated language, for example, that the A-valued graph is reflexive and is symmetric in the A-valued sense, because these two parametric sentences express that. It's easy to see also that the 0-1 law holds for evaluate variable bounded infinitary logic. So we may take evaluate logic infinitary where only finitely many variables are used. And through the translation, we again get the 0-1 law, because the obvious generalization of the translation of this logic falls in variable bounded infinitary logic. And we know here the 0-1 law holds. And also the classical results on variable probabilities, which depend on the size of the universe, transfer automatically through this translation to the A-valued case for finite A. Moreover, in the proof, in this proof that I described by just chair reduction to the first order case of the many valued 0-1 laws, lurks a random model, of course. There is a A-valued random model, in which the value of a sentence is A, if and only if the limit probability that it takes value A is 1, the asymptotic probability. Just take the A-valued model, which corresponds to the countable omega categorical random model of the class K that I described before in the translation. Then immediately the probability of that phi is A is equal to 1, as I said before, if and only if the probability that the translated phi super A sentence takes value 1. And that happens if and only if the random model in the classical size satisfies the translated sentence. Okay, but we know that this is equivalent by the translation to the fact that the original sentence takes value A in the model that we have found, which is just the correspondence to the random model in the classical side. Now, the extension axioms which define the random model in the classical side of the interpretation are usually not expressible in the original logic. This random model is rarely describable in the original logic because it may be very poor in expressive strength. But anyway, these extension axioms and the random model, the classical random model itself, do not depend on the measure utilized to calculate the asymptotic probabilities. Thus, this is a very important fact which is not very much noticed and is almost invisible in the two-valued case. The asymptotic value, truth value A, assigned to phi by the 0-1 law is independent of the measure, at least if the measure assigns positive probability to all values. Now, the most important question for me in this moment is, do all values of the algebra arise as asymptotic values through the 0-1 law? A first approximation to this question is given by this lemma. If you take any term in the signature of the algebra and you take the infimum of the values of the term in the algebra and the supremum of the values of the term in the algebra, which exist because the algebra is finite, they are asymptotic values, always. This means, for example, that if you take the Lukasiewicz chain of n+1 elements, all the values of the chain are asymptotic values of the corresponding logic. Because using chain connectives, for example, it's very easy to see that the rational k over n is the minimum of the term k times b to the n plus, in the chain sense, the negation of b. donde b to the n is iterating the chain operation of multiplication, and k times is iterating the chain addition. This is very easy to check if you make a drawing, for example. And also, all the values of the Gödel chain of n+1 elements are asymptotic values of the corresponding logic, because any element may be constructed as the minimum of certain term. Just the terms that I define here inductively is a matter of checking what I am saying. But there are logics where there are not all values of the algebra appear as asymptotic values. This theorem says that for a large family of logics, there are very few asymptotic values. If you take an algebra, which is a distributive lattice with some sort of negation, which satisfies the Morgan laws, and this kind of idempotency for negation, and moreover, the 1 and 0 are the negation each one of the other, then the only asymptotic values of the corresponding logic are these 6 values I am describing here: the minimum, the maximum, and this suprema of the this conjunction, the infimum, the suprema of this conjunction, the infimum of this conjunction, and this. This may be proved using a kind of quantifier elimination.
Sorry,
and then we get that the asymptotic values.
You have 8 minutes left. Sorry, just so you know, so you keep it in mind.
1 minute, okay.
8, not 1. 8.
Ah, okay. 8 is too little. Okay, then we may verify easily that you take the fragment of this finitary Lukasiewicz logic, based in this Lukasiewicz algebra, n+1 elements, then the only asymptotic elements of this algebra, this logic, are 0, 1, half, 1, if n is even, and these 4 values is n is odd, and that is independent of the size of n. And also for Gödel logics, the asymptotic values of this fragment of the Gödel logic corresponding to any finite Gödel algebra, any one, are only 0, delta, and 1, where delta is this one described here that happens to be the minimum element of the Gödel algebra when you look at it as a Heyting algebra. In linear Gödel algebras, it's just the first positive element. So as seen in the examples, some of the 6 values mentioned in the theorem may collapse. But for finite Boolean algebras, which satisfy the condition of the theorem, they reduce to 0 and 1. For the Morgan algebra, they are most 4. They may be 2, 3, or 4, as in the previous examples. Moreover, the conditions on the theorem are preserved by products, and order reversal is very easy to check. And then we may get, for example, this algebra for which the corresponding logic has the 6 distinct values. Similar results could be obtained under more general laws for the negation, idempotency laws. Now comes what I think the most interesting result that we want to report. Consider Lukasiewicz predicate logic determined by the standard infinite Lukasiewicz algebra, or MB algebra, and take any probability measure in the algebra and ask it to assign positive probability to any interval, which amounts to asking it to assign positive probability to any non-trivial open subset of 0, 1. Then we get this nice 0, 1 law. I am stating in 2 ways because 2 forms of the rule are very relevant. For any sentence phi in Lukasiewicz logic, there is a unique number A in the interval in the true value set, such that the limit of the event that the distance between phi and A is less or equal than epsilon is equal to 1, no matter which epsilon is. So in an approximated sense, the asymptotic value of phi is A. The second way of stating the law is simpler. For any open neighborhood of A, there is a unique A, such that for any open neighborhood of A, the limit probability that phi belongs to that set is 1. Again, in this case, it's very important, the asymptotic value A assigned to the sentence phi is independent of the measure we are using. Could be Lebesgue measure or any other measure which is positive in open sets. Another formulation of the law, which is closer to the original 0-1 law, is that for any sentence phi, an open set B, the probability that the limit probability that phi belongs to B is either 1, there is a mistake here, is either 0 or 1 that we have to correct. There is no mention of the value here, you see. However, the three formulations are equivalent, and it's very easy to check that they are equivalent just using basic probabilistic considerations and the compactness and the Hausdorff properties of 0-1. The compactness is needed for the existence of A, and the Hausdorff property is needed for the uniqueness of A. Now, the actual proof of the theorem follows the same lines of the classical proof that Professor Grede explained also, but in the context of Lukasiewicz predicate logic. We need the expressibility in Lukasiewicz predicate logic of the a sort of approximated extension axioms, and which happen to have asymptotic true value 1, and which determine a complete omega categorical theory in this Lukasiewicz logic. Moreover, we had to use model theoretic properties as compactness of the logic and back and forth characterization of approximated model equivalence in Lukasiewicz logic. This is not very well known, but we have been able to prove it. Now, what happens with the asymptotic values of Lukasiewicz logic? Again, we have, as in the finitely valued case, that the minima and suprema of terms are asymptotic values. This gives immediately that all rationals in the interval are asymptotic values of Lukasiewicz logic. Moreover, similarly to the finite case before, the asymptotic values of this fragment of Lukasiewicz logic are only 0, 1/2, and 1, as in the even case of the finite Lukasiewicz logic, finite value. Now, this is a big question for me. Do those Lukasiewicz predicate logic has irrational asymptotic values? I don't know. I presume no. But one has to be careful because Lukasiewicz logic with product satisfies all these 0-1 laws I have been explaining also.
Sorry,
but has irrational.
1 minute. 1 minute, sorry.
1 minute, but has irrational asymptotic values. For example, this value. Final comments, so I am on time. I believe the 0-1 laws generalize to logic defined by compact topological algebras and measures assigning positive probability to open subsets of the algebra. In this form, for any sentence, this form of the law holds. For any open B, the probability that the value falls in B is either 1 or 0. And if the algebra is Hausdorff, we get the unique A, for which the probability that it falls in any neighborhood of A is 1. This includes what I explained before about finite algebras. And it would include certain countable algebras with positive probability for all A. And these are the big question for me. Another big question, What happens about together logic? Does it have a 0-1 law? I don't know. What happens about Lukasiewicz logic with product and residual for product? I don't know. The problem here is that in Lukasiewicz logic and Lukasiewicz logic with product, all the connected define continuous operations. And this is part of the proof. And here we have no continuous operations in these two logics. In the first one, negation and implication are not continuous. In the second, the residual is not continuous for the usual topology of the interval. But perhaps there are other topologies where we could repeat the proof. I don't know. And this is a very last observation. The set of asymptotic values that sentences take in a logic A is an invariant of the algebra because do not depend on the measure used. But it's also a subalgebra of A. This is very easy to check. Would be nice to characterize this algebra. Okay, that is all. Many thanks.
Thank you very much. And with that, we have to go directly into the break. Sorry for that, that we don't have a question time, but please, if you have any questions,